Hi, everyone. Welcome to another session of online causal inference seminar. Today's format is the Young Researcher Seminar, which means that we're excited to have two speakers. The first speaker is Jinzhou Li from Stanford University, talking to us about root cause discovery via permutations and Cholesky decomposition. And our second speaker is Yuya Wang from UCSD, talking to us about learning treatment effects under covariate dependent left truncation and right censoring. And today's Q&A is handled by Jingyuan. Jingyuan, please take it away.
Yes, this is basically very simple. Don't use the chat function for your questions. Please submit your questions through the Q&A box, and I'll bring the questions to the speakers. I think Yuyao is joined by her collaborator, Ronghui Xu, and she will also be able to see those questions and answer it through Q&A. Okay, without further ado, Jinzhou, would you like to start sharing your screen?
Yeah, sure. Yeah, sure. Can you see the slide? Okay, cool. Okay. Good morning, everyone. I'm very glad to have this opportunity to present this work on root cause discovery in this seminar. So actually, there was a talk also for related topic like 2 years ago by Dominic Jensen. I actually attended his talk and it was very nice, so I recommend if you didn't. In Dominic's talk, like he said, the focus is more on defining a clear concept of root cause analysis, and is more about some contribution analysis. This is a bit different from what I will talk today. In my talk, the problem I will present is pretty concrete, and I will present a method to solve this problem. So this is a joint work with Benjamin, Ines, Julian, and Malus, and we have our draft and archive. Ines and Julian, they are computational biologists, and they introduced us to this interesting problem. So this problem, the motivation of this problem is from real disease, from the gene impression data of real disease patient. Sorry. So the background is like a real disease can stem from mutations in a single gene. This is also known as monogenic disorders. And the expression of this gene, because of the mutation, will be affected, and the other downstream genes will also be affected. So this will lead into many aberrant gene impression levels and also the disease. The question we're interested in is that can we use this gene impression level to identify this disease-causing gene? This is also what we call the root cause. So this problem is like finding some ultimate cause of an observed effect. It's like we already see like some people get disease, and we want to find the cause of this disease. I will present like a more concrete statistical model later. There are several challenges for this problem. The first one is that due to this propagation of the effect, many genes will exhibit aberrant expressions. So simply from their expression levels, it's not clear which one is the root cause. The second is that first of all, this problem is actually not that difficult if the causal ordering or the causal tag is known. But the thing here is that the causal ordering or causal tag of genes is generally unknown, and it's also well known like these kind of quantities are very hard to estimate, or they are generally identifiable. The third challenge is that different patients may have different root causes. So this requires us to do root cause analysis in a personalized manner. That is, it's like we only have one interventional sample at a time. And the last challenge is that the gene impression data is like high dimension. So now I will present the statistical model and present more formally about the problem. In this work, we consider linear structure equation model to model this gene impression levels, and this is more or less reasonable if you do the log transformation and the gene counts. So we have two models. The first model is for the healthy individuals. It's just simply from some standard linear structure equation model. Then for the patient, we have this extra mean shift intervention term. And this intervention term will have only one non-zero entries, which models the mutation that results in overall underexpression of the gene. Like for other quantities, this small b is just the intercept term, and capital B is a matrix encodes some DAG. So we assume there is no circle. And for the error terms, we assume it has mean zero and some diagonal covariance matrix. This means we assume there is no latent confounders in our setting. Throughout the talk, I will use this small r to denote the root cause. Our goal here is that the setting here is that we will have n ideal observational samples from this first model. This is kind of like the data of healthy individuals. And we will have only one interventional sample from the second model. What we want to do is we want to use this n ideal observational samples as a reference and figure out which variable is the root cause for this interventional sample. So this is like we want to find out the interventional target of this one interventional sample. To make it more concrete, to give a concrete example, and this example I will also use this through this talk. We consider only three variables, then one of the observational model can be like this. So in this case, then this small b, the intercept term will be zero, and we have this covariant this matrix B encodes the causal DAG shown here. And then for the interventional model, if in this case x2 is intervened, then we will have this mean shift intervention with the second entry being non-zero. This plot shows the data we will get. Here the gray points shows 100 ID observational samples generating from this first observational model. And this blue points represent one interventional sample generated from this interventional sample. We can see that x1 looks normal compared to the observation sample, but x2 and x3 looks aberrant. This is because if we look at the DAG, we see that x3 is influenced by x2. So if we intervene x2, x3 will also be aberrant. And our goal here is that we will use these gray points as reference, and we will figure out which one between x2 and x3 is the root cause. There are some related works in the existing literature. So these works either focus on directly estimate the interventional target, or their goal is to actually estimate the causal DAG, but with some estimated interventional target as a byproduct. But the problem here is that this method relies on aspects of the interventional distribution. So they rely on either second moments or likelihood or the entire interventional distribution. So we cannot use this for a problem because we have only one interventional sample. With one interventional sample, at most we can use the first moment of the interventional distribution. To our knowledge, there is no formal method that currently exists to address this problem, where there is only one interventional sample and the causal ordering may be unidentifiable. Before presenting our main method, I will first discuss this commonly used squared z-score. This squared z-score just the marginal score for which we use the variable k of the interventional sample minus the estimated mean and divide the estimated standard deviation from the observational sample. So this kind of quantify whether this variable is aberrant compared to the observational sample. Intuitively, this term will not be able to help us to identify the root cause because causality is not taken into account for this score. But it's like what we will do is that we will formally characterize under which situation it can help to identify the root cause and under which situation it cannot. So the result is the following. If we let this alpha r to k be the total causal effect of xr to xk, then we can show that if the variance of xk, recall that r denotes the root cause, then we can show that for other variable k, if its variance is larger than the product of this total causal effect and the variance of the root cause, then we have the following holds. Then when the observational sample and the interventional effect tend to infinity, the probability that the root cause will have a larger squared z-score will tend to 1. Here we let the interventional sample go to infinity because we have only one interventional, we let the intervention strength go to infinity because we have only one interventional sample. And we use this, basically we use this one interventional sample as an estimator of the mean, but its variance will never vanish because we have only one sample. So we have to let the interventional strength go to infinity when analyze whether a method is reasonable or not. So basically, the first result shows if this condition holds, then use the squared z-score can be good because it will have a larger score than the other variable. And on the other hand, if this inequality is reversed, then the root cause will have a smaller squared z-score than this variable k. If we go back to this three variable case, in this if we treat x2 as the root cause, then for this example, this condition will hold. This x3 will have a smaller variance than the second product. If we go back to this theorem, so it satisfies the second condition. So we expect x3 will have a larger squared z-score than x2. And for all other cases, if we treat x1 as a root cause, or we treat x3 as a root cause, or if we compare x1 to x2 when treat x2 as a root cause, the first condition will hold. So we will expect this is the only case that we cannot identify the root cause. And this is the result which verifies our expectation. So here I have three plots corresponding to x1 being the root cause, x2 being the root cause, and x3 being the root cause. And I generate 10 interventional samples for each of the case. And we can see that under this y-axis means the squared z-score, and the different shape means different variables. And the red color means this variable is the root cause in this case. So you can see that for the first and the last case, squared z-score indeed has a larger using squared z-score indeed gives the root cause the largest squared z-score. But in the second case, the root cause didn't have the largest squared z-score. So meaning that we cannot really identify this in the second case. We also have some like sufficient conditions such that the root cause will have a largest squared z-score than all the variables. But I think I will just skip this due to time constraint. For example, one of these conditions is that if the causal deck is a polytree, then the root cause will have the largest squared z-score among all the variables. But the general information here is that using squared z-score can identify the root cause in some cases, but not in general. Okay, so now let's actually at this point it is not even clear whether the root cause is identifiable based on the observational distribution and the first moment of the interventional distribution. Here we focus on observational distribution because we have an NIID observational sample. So theoretically, we can estimate this distribution. But we focus only on the first moment of the interventional distribution to discuss identifiability because we have only one interventional sample. We will give a positive answer to this problem. That the root cause is actually identifiable based on these two quantities.
I'm sorry to interrupt, Jinzhou. There was a clarification question, which I think is related to the slide that you just passed. Do you here assume you observe or know which sample is the problematic one?
Yeah. We assume we know which sample is a problematic one. Yes.
Know which
So
one
it's,
it is.
yeah.
Okay. Is this method that or this whole setting, will it be generalizable when you have multiple problematic samples? Because you're talking about, the first moment of this interventional distribution.
Yes, like So so for the first question, yes, we know the problematic sample. It's like in this case, we know like which samples are the gray one. We know which samples are the observational sample and which sample is the interventional sample. And for the second question, when we have many interventional sample, currently we just do this like case by case. Like we didn't use all the interventional sample together because they are like not identified. They are not from the same identical distribution. So we can only do this case by case, but we can. So it's just apply our method to each of the interventional sample.
Okay, thank you for the clarification.
Yeah, thank you for the question.
Sorry about interrupting you.
Yeah, no problem. Okay, so let's go back to this identifiability result of the root cause. So from now on, we focus on the population quantities to address the identifiability questions, and I will then present the sample version of the algorithm later. So first, we know that the population version of the z-score can be written as this form. It's just use the mean of the interventional sample minus the mean of the observational sample, then multiply by some like a diagonal of the standard deviation of the observational distribution. Then our key term can be kind of seen as some generalization of this term. We just replace this inverse diagonal matrix by this lower triangular matrix, this LX inverse. This LX is from the Cholesky decomposition of the covariance matrix of the observational distribution. So to give some motivation why we focus on this key term, we consider a case where like variables are sorted by causal ordering. So these first two lines just recall like based on these two linear models, we can calculate the mean. We have formulas for the mean and the covariance matrix of X and XI. So in this special case where variables are sorted by causal ordering, we know like this matrix B will be lower triangular. Therefore, we can write down the formula for this lower triangular matrix Lx based on Cholesky decomposition. It's just this form. And then for this target quantity, key quantity we just introduced, we can see that it will have this following form where there is only one non-zero entry, and this only one non-zero entry will happen to be the root cause. So in this case, the root cause is identifiable based on this quantity, because it is only one non-zero entry here. And note that for this quantity, we use only the first two moments of the observation distribution and only the first moment of the intervention distribution. But of course, in general, variables are not sorted in a causal ordering. So this means this matrix B is generally not lower triangular, which means this lower triangular matrix from Cholesky decomposition does not equal to this formula here. And also means that this Causal may not have this previous informative form where the only non-zero entry is the root cause. But what is nice is that the root cause is still identifiable because of this result. And this result is actually from some linear algebra results. So let's look at this theorem. This theorem says that let the variable be sorted in any ordering, not necessarily a causal ordering. Then for this key quantity I just presented, if this Causal has only one non-zero element, it must be in the position of the root cause. So this gives us the identifiability of the root cause, because then we only need to try all the permutations. Then for sure we can find at least one permutation, which is a causal ordering. For example, causal ordering, such that this Causal will have only one non-zero entry, and then this entry must be the root cause. So this gives us, this shows that the root cause is indeed identifiable in this setting. And this result also shows that the root cause is identifiable even when the causal ordering is not. So in this sense, discover the root cause seems like a simpler task than estimate the causal ordering. Okay, and this identifiability result actually can directly motivate a sample version algorithm. And so the sample version algorithm, we just need to try all permutations. Then we estimate this Causal pi. Now I make the dependence of pi of Causal and this permutation pi clear. We just need to permute the variables, then calculate this the corresponding lower triangular matrix here, and like we estimate this from the observation distribution, and we use the interventional sample as the estimation for this for the mean of the interventional distribution. Then we have this estimator for this Causal pi. And based on Causal pi, we can obtain a set of potential root causes, because we expect if a variable is a root cause, it is the only non-zero entries. So it should have the largest absolute value. So we will just check and put all the variables that has the largest absolute value for the for a certain permutation pi into some set. Then in order to quantify the extent to which this Causal hat pi exhibits the only one non-zero entry, we will use the largest entry of this Causal hat pi minus the second largest entry divided by the second largest entry. So this can quantify this pattern, because if Causal really has only one non-zero entry, then the second largest element will be very small. So this C hat will be pretty large. In the end, we can obtain our final root cause score, which we call the RC score for each variable as following. So if the variable is already in this U hat, if the variable is already some potential root cause, we just assign it the largest C hat pi for the pi such that this variable has the largest value of this Causal. Otherwise, we just set it to some this WI to C mean. This WI is just some weights based on square Z score, and C hat mean will make sure the variables not in U hat will always have a smaller value than the variable in the U hat. This result shows that the sample version algorithm is valid. This shows that if these two estimator from the observation distribution is consistent, then as some observation sample size and the interventional strength go to infinity, the root cause will have the largest score than other variables with probability tending to 1. Then we go back to this 3 variable example. This first row is the previous result by using squared Z score, where it cannot identify the root cause in the second case. And the second row is our new RC score. And we can see like now our method can identify all the root causes, because the red variables are always has the largest value. Okay. Of course, this method has one issue here, because it requires to try all the permutations, which is of course infeasible when P is large. And the reason here we need to try all the permutations, because we want to find one, let's say, good permutation that can give us this only one non-zero pattern. And so in order to reduce the search space of permutations, we need to understand which variable, which permutations are good permutations. And so we give a characterization with this. We say a permutation pi is good. Here good again, this good means the corresponding population term Cauchy pi will have this only one non-zero pattern. So this shows that a permutation is good if and only if the parents of the root cause are positioned before it and the descendants of the root cause are positioned after it. So this result is actually very useful for us to propose an efficient algorithm, because let's say if a set D, which contains the root cause and the descendant of the root cause, if this set is known, but we don't need to know which one is the root cause in this D, then we can generate the following like D cardinality number of permutations, and then we know that one of them must be good. This permutation are generated by, we just put the remaining variables not in D in the front position. Then we put each variable one by one, like in the second available permutations, and the remaining variables then in other positions. Then you can know that at least in one case we will put the root cause in this second available position. Then in that case, it will satisfy this condition, the theorem in this condition, and this permutation will be a good permutation. Of course, we will not be able to know which variable is the root cause here, but and so we don't know which permutation is good. But what we know is that one of the permutation in this D-cardinality permutation is good. So that this is kind of enough for our purpose to reduce the search space of permutations, and this
Sorry
D.
to interrupt, Jinzhou.
Yeah.
You have 3 more minutes. That would
Yeah,
be
sure.
great if you can add. Thanks.
Yeah. Thank you. This set D is of course generally unknown in practice, but what is good is that it can be estimated because it contains the root cause and the descendants of the root cause. So we expect it will contain all the aberrant variables. So we can just estimate this set using all the aberrant variables. Based on this, we actually proposed a faster and valid algorithm for root cause discovery. So by this, I just want to show that the computation is not a very big issue for our method. So in the end, I want to go back to the gene impression data that motivates this work. So this data set contains RNA sequencing read counts from skin fibroblasts, and we have high dimensional data set, and we have 58 patients with this Mendelian disorders. So we to discover the disease causing genes for these patients, we based on our previous method, we then propose a heuristic high dimensional algorithm, which we also need to use some dimension reduction technique, because the reason here is that this L is actually pretty hard to estimate in high dimensional settings. That's why we need to use some dimension reduction technique. But the thing that our heuristic high dimensional algorithm actually performs pretty well. So this is one result. This is one result for one patient, and I have 3 plots here. The first is the raw gene impression levels of this patient, and this red point denotes the root cause. We can see that if we look at the raw gene counts, we will not be able to identify the root cause because it kind of varied among all the other variables. If we use the second plot, shows the result of the squared z-score. If we use the squared z-score, we cannot identify it either because it's still buried. And the last plot is using our method. And in this case, we can see the root cause really stands out, that we can kind of identify it for this patient. And this table shows all the results for all the patients. So I think in general, our method performs quite well. For example, in this patient, our method will give the root cause the largest score, but the square z-score just not working. But of course, our method is not perfect, that it does not work very well for these last few patients. So there's still room for improvement. So this work is like one the kind of like the first step for this problem, and there are many directions can be explored. For example, how can we deal with the multiple root causes? How can we deal with latent variable setting and nonlinearity and or cyclic graphs? And it's also interesting to investigate whether this idea of using permutation and Cholesky decomposition can be kind of used for structural learning or active causal learning when some interventional sample is available. Yeah, so that's all for my talk.
Yeah.
Thank
you,
you.
Jin.